So thank you everybody for coming to my lecture today. I met Armen in the Huawei building here in Moscow when I was coming for a visit, and he kindly offered to give me a chance to speak to you and get to know you a bit better. And so I'm going to give a talk today a little bit about some of the research and work I've done with deep neural networks. Put your hand up if you've heard of deep neural networks. Okay. Has anyone here used deep neural networks? Okay. So last time I gave a lecture in Russia was about 3 years ago, and I tried to present some big ideas, and the guys from Moscow State University, they said I didn't have enough proofs in my lectures. So this time I have a lot of different proofs, but I don't know if it's going to be the right audience for this. Are you guys all doing a kind of business course with informatics, is that correct? Yeah. All right, okay. So this might be a little bit maths heavy. I'll try and just introduce the big ideas. But so when I was working for Amazon in Berlin, we had a little bit of a problem that the business people didn't really understand what the scientists were doing, and the engineers also didn't really understand what the scientists and researchers were doing. So maybe for you it will be useful to see a little bit how researchers in AI think and what they do. And at the end, I'm also going to show a little bit, so I'm going to talk about 3 things today. One is going to be essentially some kind of theoretical framework that I devised during my time at Oxford, and I continued during my time in Huawei. And that's just being published now in the Journal of Machine Learning Research. I'm going to talk about some algorithms that were also developed, and I'm going to go to the end with a product that I'm developing now, which is one of the reasons why I'm here in Russia. So I'm just going to give a little bit of a background in statistical learning theory. So for an input-output pair x, y with the prediction function h, and then which is parameterized by a weight vector w, we have a loss. Does this all look very complicated? Put your hands up if this is too complicated. Okay, so are you guys familiar at all with classification? Yeah. Okay, so imagine that like my x is just a picture, can be any picture. Let's say it's a picture of a dog. Then y is like my output, which is like, is it a dog or a cat? Yeah? And so I have some kind of, I'm just trying to learn a function which takes my input x and converts it into my label. That's how I classify things, that's how it works. Right? And the loss is basically just like how wrong I am in what I present. Okay, does that make more sense? Okay, cool. So basically, shall I skip this and go to simpler things?
I love to hear you, so...
You know what, I'm just going to continue, and if you guys have questions, maybe you guys just ask me that at each point, all right? Okay, so I've just explained the x is basically your picture, the y is like your label, so is it a cat, is it a dog, is it a person? And what I'm trying to do, this is the essence essentially of all machine learning, is learn a prediction function which takes my input and gives me the output that I want. That's why it's called machine learning. And so you measure basically how well you've learned what you learned by how low your loss is. That's basically just machine learning. And so the thing is like the loss can be defined on several things. So if you had all the data in your world, you would have essentially this thing called like the true risk or true loss, which is just the expectation under your data generating distribution. Over your entire data set, you have this thing called the empirical risk. And if you just have a mini batch of data, you just take a subsample of your data, you have this thing called the batch risk. And now, the insight that I had, so who here has trained neural networks, ever? Okay, so what's like one of the most important things when you train a neural network?
The amount of layers.
Okay, so that's like the architecture,
yeah.
Right? But when you train it, is there anything else you have to set?
Data.
Okay, you have your input data. Anyone else? Anything else?
Bench size.
Okay, one more?
Optimizer.
Yeah, okay, but what's like the setting of your optimizer?
Learning rate.
Exactly. Right, so do you have like a pen here or something? This is very impromptu. I've got this. Can I do this here? No? Can do it here. Well, I'll do it on this, it'll be fine, right? So imagine that I'm here, right? And I'm trying to get to this bottom bit there, right? If I move like a tiny, tiny amount, I go here very, very slowly. Yeah? And if I move too much, I can like bounce out like this, right? So there's this parameter called like the learning rate, which is basically how big your step size is. And that's basically the most important parameter in neural network training. Now it sounds, it's cool I did it already, right? Now, it sounds kind of trivial and stupid, but actually, so people at Google, Facebook, Yandex, Huawei, they spend millions and millions and millions. I've already done it here, it's okay, yeah. Okay, so I will do it again. So you have this thing, and you're here, and you want to come to the bottom, and if you move with a very small learning rate, you get there very slowly, right? But if you move with a big one, you like come out, right? And so this is obviously like a very simple example, because in the real world, it actually looks something like this. And if you maybe move with a very small one, you stay here and you want to be here, or you want to be there. So the point that I want to make is that even though it seems like a trivial thing that you just choose a number for in practice, when people are running for competitions, they run their experiments with neural networks thousands or millions of times. So this is why like the biggest companies have the best results, because they just have the most resources to try the most combinations. And even though there was all this work on how I decide my neural network and what I do with my data, the way that people were choosing their learning rate was really just by making it up. They tried it, see how it did it again, and there wasn't really much theory behind this at all. And that was kind of where I decided I was going to contribute to the community. And so the intuition that I had, basically, as you can see on this diagram, how big your step you can take kind of depends on the curvature of this surface. So if it's like a very sharp one, you can only move a small amount until you start coming out. And if it's very, very flat, right, you can move a much bigger amount, right? And this is basically known as the curvature. So it would be like nabla squared of the loss. That defines the problem. So my insight was that if I could look at how the curvature of this batch risk was different to that of the empirical risk, if I could have a theory for that, I could basically say how I should change my learning rate as I change my batch size. That was like another problem. So people, you have a big computer with 8 GPUs and you train your network, but now you want to train the same network on your phone. You can't use 8 GPUs, you've only got one small one, so I have to change my batch size because I can't fit that on my phone. But now I have to change all the parameters. Do I do like a grid search again? So that was basically the work I had here. Now, the maths is somewhat complicated in detail, but the idea is actually very simple. The idea is simply that I can just rewrite this batch Hessian, which is just, as I've said, the second derivative of the risk, right? That's just this, the Hessian, right? I can just write it as the empirical Hessian plus some perturbation term, right? That's just, I've just defined it that way, you can say. And in expectation, I know that this term will be 0, and it'll have a variance given by this factor, right? And now my insight, because I was very interested in maths, I did an undergraduate in physics, was that if I made like a few extra assumptions about the nature of this term, this matrix would basically be a random matrix. And we know a lot about the spectra of these random matrices, and because we know a lot about these matrices, we also know what these matrices look like if I add something to it. And that will give me the entire theory. And that was basically it. And so all this next math stuff is basically just doing that, right? So it's like a little bit complicated in detail, but basically what you cannot have is these elements here, they cannot be too dependent, right? There must be some level of independence, otherwise the matrix will not be random. And the variances cannot change too much, and they must not be infinity. And then basically this matrix, its eigenspectrum, converges to Wigner's semicircle law. And that's basically it. And once I have this, I have a relationship to how the largest eigenvalues of my batch are related to that of my mini-batch. So that's essentially it. Now you can say, okay, like why is this interesting? Like for me, it was just interesting because you can then see it. So who here is aware of CIFAR 100 or CIFAR 10? You guys heard of that data set? Okay, you heard of the VGG network in Oxford? Cool. It's getting a bit old now, but back then it was. So this is just, sorry?
Did it work for all optimizers?
Yes, but we're going to get there in 1 second. So what I've done just now has nothing to do with the optimizer. the theory is completely optimizer free. It doesn't matter where you are in weight space, it is always true, but it's like the application is a little bit different depending on the optimizer. So I'm going to get there in 1 second. So I just wanted to show you that this is exactly what happens. So all I've said is that for your mini batch, if I use a subsample, that like the largest eigenvalues get larger, right? And you can see this exactly here. So with the full data set, the biggest eigenvalue is 11.41. If I just use a subsample of 128, that's now 80.15. And the same is true also for the smallest. The smallest also gets smaller, right? And so that was very nice to see that in practice. Now I can do something a little bit more complicated. This is just an algorithm to calculate the Hessian variance, which is basically just this term. And you can see how we fit here with theory. So this is using the full data set. This is then the average of the mini batch, and of course it's stochastic, so we've averaged it over 10 runs. This is one theory, the one I've showed you, and this one here is a little bit of a more complicated one that I'm not going to go into detail, but if you're very interested, I have a 60-page paper with proofs, and you can read that in your weekend and spare time, maybe over a beer. So this is basically what happens. When you have a very, very small mini batch, your largest eigenvalue is out here, and as you increase the mini batch, it decreases nearly proportional to the amount of decrease. But once you've already decreased it by a certain amount, by essentially increasing the mini batch size, it just doesn't decrease by that much more. And this is for one model, this is for the more complicated model, result is the same. Now back to your question, you said which optimizer were you interested in? SGD, Adam, what do you use?
SGD, yes, and maybe more. I don't remember really. My last name network was a few months ago. But I have another question.
All right, go on.
Did you decide that moment that, as I know, in nets we have this kind of problem that net is like working, then we have overfitting, and after some time we have the best score. Like it looks like that. Yes. 1 second.
Do you want to come up here and maybe draw it? All right. We'll do this here. Go.
So, as I know, in nets we have this kind of problem. But it takes a lot of time, really. So we fit our net, so the score goes down, yes, the loss. Yes, then we have overfitting, and after some time it goes better, and maybe we can get a better score. Do you know?
The double descent phenomenon.
Yes.
So actually it's interesting because there is some theory on this double descent phenomenon. I was personally never super convinced by it. Usually they have this in terms of like the network size, right? They usually have this in terms of like the amount of parameters in your network, right? There is actually the type of theory I was working with now is a little bit what they use here. I've actually never seen it in my own training. I think they do, if you look very carefully at the experimental details, it's not really what people use in practice. In my understanding, if you use like a good set of parameters, it usually does something like this. It also depends on the data set you use, right? So for example, I've never seen the double descent phenomenon on something like ImageNet. Usually it's something like MNIST or CIFAR10. So for like big image type problems, essentially, are you aware of data augmentation?
Yes.
Okay, so do you guys know why data augmentation works?
Yes.
Go on, why?
Can you repeat this?
Yeah, do you know why data augmentation works?
Yes, because we just made our data set bigger.
Do you? But it's the same data.
It's not really the same. For
Okay.
the future is like the different.
But why? So I have a picture, yeah? Let's say it's a picture of an elephant. Yeah? Okay, that's my elephant, yeah? I'm not a very good drawer. So here's my elephant, yeah? Okay? I have one picture of an elephant. Now I cut away this part. Yeah? Or I just take this crop. Or I just take this crop. Is that like two different elephants? then how do I have more data? Yeah, I'm asking you. It's a question. Go on.
For different parts of pixels, we have different filters, and different parts of elephant will go to different filters in our network.
Okay, so you're saying like this part goes to this filter, this one goes to this filter, and now as I move it around, the filter is seeing more different things. Okay, but if it's the same, so if I put it then back in the same place and I just have zeros here, I don't have that. That is one form of augmentation. Go on.
Maybe we separate parts of an elephant, like we have a head,
Mm-hmm.
so which is programmed that this is a head.
Okay.
We have legs and body and tail, and when a computer sees like every part of elephant together, so he understands understand that this is an elephant, and we just don't need hold this picture, so we just use parts of that.
So actually, if you did actually that, it would probably not work, right? Because if you just see this, that's not really an elephant, right?
No,
So typically what they do with the augmentation is like, let's say this is 32 by 32, yeah? They will cut out an amount like 28 by 28, and then they will take a new 32 by 32 picture and they will just move it around. So you will have 32 minus 28 plus 1 squared, more things you see, but they're all highly, highly dependent. This argument that you've created more data is actually super weak, right? But the thing that's interesting is that we said earlier here, if I can go back, is that when you're training, all you try and do is reduce this loss, right? And you do that by learning a function that just predicts your input to your output, right? And because these neural networks are just such powerful functional approximators, they can really learn to overfit incredibly easily, right? So by showing them actually like more different cuts, you limit their ability to actively memorize that particular image. Now this is an open part of theory. If you're going to do a PhD in this, I'm very happy to read what you write. I'm sure everything I said will be wrong. But the reason I mentioned this is so I gave you this number here. So this is here is like 5 squared is 25. This is for a small image, right? If I have a much, much bigger image, let's say like ImageNet, which is like 256, and I take 224, yeah? I basically have a factor of 1,000 augmentation as opposed to 25 or more, right? By which I mean you will never really see this phenomenon. So this phenomenon was largely reported by like mathematicians working on MNIST.
So we can reduce this effect by making augmentation?
I would say when you have augmentation, you will never see this. Real augmentation and the reason I mention this is simply because what a lot of people don't understand is that the augmentation depends very strongly on the image size, right? Because if you can just flip an image, that's a factor of 2. But if I crop and move around, that factor is given by basically the input size minus the crop size plus 1 squared. And of course, if your image is very small, it will just not be that a big number. So anyway, back to where we were. You asked me about SGD, right? So this is actually here the theory for SGD. So what I basically say is when I scale my batch size or my learning rate proportional to the batch size, I expect it to work up to a threshold. So you can see here the agreement is incredibly good. And this works here for the VGG, no batch norm, no weight decay, with batch norm and weight decay. It works also pretty nicely up to a threshold. See, when it gets too big, it no longer works, as I was saying, right? Why is that the case, right? From the theory, you see this here because at some point, this term, when the batch size gets big enough, gets comparable to this term. So there's no more effect you can have. So that was just shown here. And you asked me about Adam, is that correct? Yeah. So you have, and so yeah, this is just another thing. So this allows me to automatically learn the learning rate as I go through instead of hand tuning it. Also quite a nice result. But yeah, for Adam, it's a little bit more complicated. So this is actually a paper I found very interesting, so you guys can see what real science is like. It was published at ICLR. So do you agree with me that this blue curve and this red and green curve do not really match? Who thinks they match? Put your hands up if they match. Put your hands up if they don't match. Yeah, okay, so I fully agree with you. I think the person that published this was a moron, or maybe they're not a moron, but these two curves do definitely not match. And so that was basically the prevailing theory, is that we should also get this linear rate for Adam, and the reason we can show this linear rate is because the red curve matches the blue curve. And now the beauty is it worked so badly that for the final curve, they actually messed around with the experiment and reduced the learning rate again to get it to match. So I definitely knew there was something a little bit dodgy in this story, and this was somewhere where my theory could add. So the algebra here is a bit long, but do you understand how Adam works? What's the difference between Adam and SGD?
Yes, remember, maybe I remember. I think it was like, no, I can't say.
Okay, so for those of you, a lot of you never heard of Adam, right, I imagine? Is that right? Okay, cool. So do you guys know like Nesterov and Polyak? They were like very famous mathematicians in Russia. They basically invented optimization. Does that mean anything to you? Okay, cool, right. So basically like optimization is just the field of getting this function down as close to 0 as you can, right? It's just optimizing on my training set, yeah? Getting my loss to 0 in my training set. And there are like different algorithms to do that. The simplest, which is just SGD, is I simply, if I can do this here, I simply have my loss, right? And at some point, I just take a gradient. And now my new weight is just my old weight minus some learning rate of the gradient. Yeah? That's just called gradient descent. And if I don't take all my data, but I just take some of my data, it's called stochastic gradient descent. That's the simplest one. That's what we were just looking at now. Now you can do, of course, more interesting things, right? Because maybe in one direction you're like this, but then maybe in the other direction you're like this, and one you're like this, right? Very sharp. So you don't want to take the same step in each direction. You want to have maybe, for one direction you have a big alpha, for another one, like you maybe have a smaller one, and so all these things. And this is basically what Adam, which is like the most popular optimizer in deep learning, tries to do. And the thing is because of this, you end up in quite an interesting situation, which is if you're wrong about the direction, but you're more wrong, where is it, here, than you are here, potentially, you end up not with this linear scaling rule, but you end up with the square root scaling rule, basically, right? And so, because this isn't really like a maths class, if you guys are interested, you can just look at my paper and send me a message, right? And we can just talk about it more. But that's basically what I showed here. Do I have it there? Yep. I have this square root scaling rule that goes very well up to a threshold when it starts to not work. And that's because essentially at some point with a small enough batch size, doesn't matter how wrong you are by a constant factor, this will overwhelm this term for small enough b, right? This just goes to infinity quicker than that does. And that's it. And so that's basically the entire theory. This is just some experiments to show that it works that way and that it doesn't work if it's linear, and some more intuition stuff, and we're going to just move on. Do you guys have any questions? Okay. Any questions about deep learning in general?
How is life working with overfitting?
I should have done that in this talk. What, with the optimizer or what in general?
In general.
What do you mean, like, does deep learning overfit?
No, I know, but is it like helps to solve this problem? Why not?
The next problem I'm going to do now does specifically work with overfitting, but yes, it does, because actually you can see here that the choice of my learning rate has an effect on not just my training accuracy, but on my validation and test accuracy. So it's actually very easy to train a neural network. Basically, any learning rate that isn't too big will work to train. But if you want one that will generalize good to unseen data, the choice of the optimal learning rate is much more important and harder. That's why these companies, anyone can just drive that learning rate to near zero and get a good training result. But that's why they run so many different examples and so many tests, because the one that's actually going to work on your held out data is different to the one that trains best. But what's interesting is actually the largest one that trains seems to do best, right? And there's some theory behind this. The theory behind this, I didn't want to go into detail, is this idea that you want a flatter minima than a sharper minimum, basically. And that if it's a very, very big learning rate, it'll jump out of the sharp minimum. Now, that intuition isn't actually completely true. I've done some proofs to show it isn't true, but the intuition kind of works. Any more questions? All right, cool. So we'll go on to something a little bit easier before I talk about something more practical. So when I was actually here in Russia, and I did an internship at the Школа Экономика and Samsung AI, so some of my compatriots, they came up with this simple technique. They actually thought they invented it, but they didn't. Polyak invented it 50 years ago. They just rediscovered it. And it was called this kind of weight averaging. And the interesting thing is, so let's imagine I'm just training with my gradient descent. Then at the very end, I can just average out my weights. And this is already a well-known technique in optimization. But what was kind of interesting was that if you combine this with very large learning rates, your optimization was not so good, but your generalization was really much, much better than anything else. And they kind of didn't really understand why that was the case. And so I basically developed a theory for this. And it gets, again, quite mathematical, but I'm just going to go with the simplest basic idea. And the simplest basic idea is just simply this. If I imagine that, again, I'm bouncing on my favorite quadratic model, right? And this is, let's say, my true risk. And the true risk is basically what would give me the best generalization, right? And at each point, my gradient that I get from my data is like the gradient from my true risk gradient plus some noise, right? Let's just imagine that noise is like IID Gaussian. Then it's obviously clear that by simply reducing my learning rate, I'm always going to end up completely stuck within like a bowl of noise. I'm never going to get to the minimum. Whereas if I go around with a big learning rate, even with the noise, and I take the average, I will end up right in the middle. And that's basically what this proof does, right? Now, the only extension of that is that the model is, of course, somewhat unrealistic, because if I move with a learning rate of 0, then clearly like the error here is going to be basically the same as the error here. So I need like some way to characterize that dependence. And that's basically all the theory that we did here. So it's just worth saying that this effect becomes more and more serious in higher dimensions. And this is actually our example where we have more and more parameters, and the difference between using this averaging, what's that? That doesn't matter. Okay, this averaging technique or not just gets bigger and bigger with more parameters. And so all we do here is we just generalize this theory to include essentially this dependence on your distance. And the result is basically the same. So if you guys are into maths, you can see the proof. And again, it doesn't actually matter how often you average. You can average every time, or every 100 times, or every 350 times, and it basically gives the same result. So this is what we have here, the experiments for this. And yeah, so this is just includes essentially that what we had here in the theorem is that the iterates in weight space need to be a certain distance apart for this to work, to have that kind of level of independence. And however, the experiments kind of showed that it did actually even better when you had certain amount of weight decay than not. As you can see here, the difference between the blue, yellow, and red curves. So the theory actually can accommodate this very nicely by, instead of having like a kernel that depends on the difference in weights, it just depends on the relative weights. So the only point that's worth saying with this is like, hey, why should anyone care about this theory? How does it matter at all? So you can actually, by using this, we were able to combine it with different types of optimizers that weren't done in the literature, and basically just get much, much, much better results than anyone else was getting. So using kind of optimization alone, we're able to get about 2% above on the very well-known ResNet 50 on ImageNet just using optimization. And most people, they will do stuff, they will ensemble, so they will train the model hundreds of times and take the average or add in different data. And we did this all just with optimization. So, and it also works for NLP. Any questions?
So pictures and NLP.
Yeah. I mean, I was more interested in the theory, so I just wanted like experiments that show that it worked. Anything else? Okay, cool. So I'm going to talk about something now a little bit more businessy that I've been working on for the past couple of months that I think Armen wanted me to make the whole presentation about it, but I didn't have time to change the slides. So back when I was here in Russia, I spent a lot of my time in the gym, powerlifting actually, and did more of that than research actually. And so one thing I would do is I would just take videos of myself lifting and I would send them to my coach, right? And then if I was lucky, he'd be there online and he'd say something, or I'd have to wait a day. And I was just kind of wondering, you know, if he didn't even need to be there, he could just see that from the video. That information must have all been there in that video. And how much of that could I actually capture myself? And how much of that could I automate? So it kind of got into my head, and this is kind of the company logo I've developed. It's called Pure Strength. I think it would be like Chistaya Sila in Russian, but apparently that sounds weird, so let's just keep it with Pure Strength. So, you know, this kind of just started playing over in my head like as something I wanted to build and make, and I know you guys are often in business students, so you'll be obviously working with products, specifically information, so maybe that's interesting. So, you know, the question is a little bit, you've got this idea of something you want to build, and like how do you relate that to AI engineering and stuff out there? So the stuff I did here is actually like, can you guys see these boxes around here? Do you know what this technique is called? Sorry? Yeah, perfect. Object detection. So the first thing I thought of doing was, okay, well, if I can move the weight quickly, it's easy. And if I move it real slow, then it's hard. So I could actually basically, by looking at the velocity profile, this is this thing here, I can basically see like how difficult it is what I'm doing, right? So that was actually very simple. I just did some object detection and some engineering to basically then, from past data, basically figure out like how difficult something is and program based off that. So that was actually pretty easy. Do you guys see this little figure here? Do you guys know what this is called? What's it called? Okay, so this is, I actually stole this software from Facebook, right? It's called Denspose. But it falls under a category called like key point and body detection. And basically, do you guys know how this is trained? Like how did Facebook do it? What?
Trackers?
Go on, try something else.
You know, they just put like trackers all over your body.
But imagine you couldn't do that. What would you do?
Maybe they just remember the like a point on your body.
Yeah, but a deep neural network knows nothing. It's initialized randomly. You need to train it. Go on.
Maybe they point it on the picture. Some people.
How do they point it?
Draw it.
Yeah, exactly right. That's exactly what they did. They took about 10,000 pictures and people manually drew on it. This is the head. This is the left shoulder. I'm not joking. This is the right shoulder. This is the foot, right? And so the neural network can actually, so I've just given you the like 2D mesh, but the neural network basically labels 24 body parts if it sees it. And so it's just worth saying, so for the bar tracking here, I basically collected the label and collected the videos and labeled it myself on my own laptop. Do you guys want to have a guess how many images I used so it was getting pretty good? A number off the top of your head. You get a beer if you get it right. You get a bottle of champagne if you get it right, actually. Go on.
50,000? 10,000?
Go on.
1 million.
2,000.
All right, and I label this myself manually.
Maybe you paid some students for that.
This guy is smart. Smarter than me. You can work for me. You can work for me afterwards. No, I used 70 pictures, right? So what do you think I did to those 70 pictures to make it work better?
You trained one network and then just adjusted its result for other 10,000 pictures.
No, go on. We spoke about it earlier.
Augmentation.
Yeah, exactly. I used tens of thousands of augmentations, cropping it, turning it around, brightness. And so anyway, I wanted to show you something. So this is just some of the stuff you can see, like, are you parallel or not? But I have something more interesting to show you. So who here deadlifts in the gym? Does anyone know what a deadlift is? All right. Okay. So in powerlifting, you have 3 exercises, and they're actually pretty prolific among many different sports in terms of strength they build. The one is like the bench press, where you just push off your chest. The other one is the squat, where you just basically have something on your back and go up, go down and up. And the deadlift, you basically just pick something up off the floor, right? And the reason this was kind of interesting to me is, like, as you can see here on 2 examples, both myself, a lot of people, when they lift this, they will really curve their back, right? Now, the jury is still out to how bad curving your back is, but most people with an understanding of spinal mechanics will tell you it's not good. It's just a question of how bad it might be. It might not hurt today, it might not hurt tomorrow, but usually over years it does cause problems. So I was wondering whether I could use essentially this kind of dense pose estimation here to basically measure when you start your lift whether your back is curved as fuck or not. That's basically what I had in mind. So now the question, here is an example of me nice and curved. Here's an example of me less curved. So my question to you is, if you had this data from your neural network, how would you, as smart business students, engineer a solution to basically figure out if it's curved or not? So of course you can see it, you can look at it, right? That's like, but you have to train the algorithm to do this, or you have to instruct a software engineer to build this solution. It has to be automated.
It's just a classification, if it's okay or it's not.
Well, that's the thing. So what's the problem with making it a classification task?
Maybe there could be a different, not binary, but...
Yeah, but it's a regression task, yeah? It's just, what?
Maybe it depends on angle and like angle.
Well, that's part of it. That's getting close to where I want to be, but what's the problem with that? With a regression solution or a classification solution? What do you need for that?
Is the output of these metric, I don't know, network is 2D or 3D?
It's a contour plot, so it would technically be 3D, but that it doesn't, like, you need to get it, like, what I'm showing you is everything you get.
Okay, 70, maybe it's 70 pictures. Augmentation maybe will not be enough.
Well, the pictures I had was just for the bar. That's a separate network that's doing the person classification, right?
Yes, there could be another network. One network will catch the frame, and another will classify.
Okay, but what's still the problem? You guys all look confused. So the problem with an approach like that is I would need to label hundreds or thousands of examples. I'd have to get someone, I'd have to do a film, and this is me doing it myself. I'm trying to get rich soon so I can travel to Moscow, have a great time, right? I don't want to spend there thousands of times saying this was good, this was bad, or how good, how bad. You have to have thousands and thousands of examples.
But we can make a clusterization model which will clusterize our pictures, find some patterns, then if these patterns will correspond to our classification, true or not true, we could...
Yeah, so you're basically leveraging unlabeled data for labeled data. But let's imagine you only had these 2 pictures. That's all you have. How would you solve it? Could you?
I just will draw a line, and then
Go on.
It will be
Draw a line between where and where?
From all the back, on the back of the person, and then if the angle will be appropriate, I will say that this person makes its training good.
Do you mind just pointing it out on here how you would do it? Come up, point it out.
Maybe I will draw.
Yeah.
хотя, ну так.
Yeah, but how do you tell the machine to look there?
Find 2 points.
So you would
here and
find-
there. Ой.
So you would find the what? The top of the shoulder
Yes, and
and here.
here.
But then it would do this here and here, and it would still be a straight line. Because if I connect 2 points, the line will always be straight.
Maybe I'll calculate the area of this and the area of this.
But how are you going to use... So you're going to say what? If I have 2 lines, and the area between it is bigger, what the hell happened?
I'll make the third point in I don't know. Okay, here, and it will be triangle.
How do we get it back? Yeah, we're almost finished anyway.
May I sit down?
Yeah, of course, of course. It was good. It was a very good attempt. I don't think it matters. We can just look at this, right? Forget this. We'll just do this. Yeah. All right. So you were actually pretty close to what I ended up doing. Yeah. So what I ended up doing was this basically very easy thing was that it's for a circle, it's just easily known algebraically. If I take essentially 2 points between it, and this is part of the circle,
I'm also a good guy.
You're back. Oh, perfect, right? So you can basically just find out from this and this curved part what the radius is of your circle. And of course, if the radius is very, very large, then you're not so curved. If the radius is very, very small, you're obviously very curved. Now, the only problem with this is going to change if you're a bit closer to the camera or a bit further away from the camera. So do you guys have any ideas of how I could fix this so that it doesn't matter how close or far you are from the camera gone?
Maybe you just put there your sizes or parameters like your height, and the program like understands how close you are.
Oh, because you've given it a fixed point of your height.
Yes.
Yeah, so that's basically what I did, but less intelligent than that. I just actually divided it through by the size of my head, right? Which is also going to change as I go further and closer. And so here you have my metric, which basically will tell me here that if it's a low value that is not very good, you're curved, and here is much better. So that's all. Do you guys have any questions? I mean, there's more stuff. I've built more than this feature. I'm not going to tell you all my secret sauce. Of course, I'm hoping to get rich with this. So,
How you found that 70 pictures with augmentation is okay? Why not maybe 20 or 200?
so that's a good point. It's like, so I started training it on less, and it was pretty bad, right? And you have to keep in mind that let's say I want to hire someone on like Amazon Mechanical Turk to do this for me, do the labeling, right? I have to set up that whole infrastructure, right? So I basically just labeled as much as I could on a few flights when I got bored, right? And then I just tried with the augmentation. And I trained it just overnight on my laptop, right? So it was just a 4 gigabyte GPU laptop, NVIDIA trained it. And at that point, it was good enough that I could continue with the other parts of the product. So if you look here, I can't actually show the video. But so the problem I had at the beginning was that these curves were not so smooth, right? And when they were not so smooth, it was kind of much more difficult for me to run algorithms to tell me, okay, when did you start, when did you stop, because of the inherent noise. So I had to smooth it, and then the smoothness, I would lose information. So it would be inaccurate in terms of how long the lift took, right? Because the more you smooth, the more you average out over the frames, and like essentially like it's like the size of your lens is different, right? So it was good enough for me to continue on other parts of the product, right? Realistically, it might make more sense now for me to get more pictures, see how good my object detection is working, and on pictures that it's not working well, have them relabeled. But that's just trial and error. So I did all this deep learning theory, but now that I'm building a product, I do no theory, zero, right?
What was the network? It was
ResNet 101, the same one that I trained here. So
101 it means
101 layers.
Okay.
So better the devil you know than the devil you don't. So I know the ResNet 101. So I was sure I could train it from scratch if I needed to.
You chose this net because of what?
Well, I knew it. It was good.
Okay.
They came already pre-trained, so I could just like do essentially fine-tuning to it. But as in, the ResNet is a very well-known high-performance network. Like I think now transformers are like taking over in many fields. But the transformers typically work very well if you've like pre-trained them on lots of data, which wasn't the case for me. Go on.
I have a question about optimizers.
Sure.
Just unfortunately, I think that most of us haven't ever heard about them, and that's why can you please tell us the main difference of optimizers, of different optimizers, CG, D, or Ranger?
Oh, right. So, yeah, okay. So, yeah, how do I put this? So basically, as I was saying earlier, when you like just are at some point and you take the gradient and you make the next point as basically the old point and you're going down towards the minimum minus your gradient, yeah? This is called gradient descent, right? And stochastic gradient descent is just when you don't use all your data to calculate this. So this gives you your SGD. And if you want me to be totally honest with you, don't waste your time with any other optimizers. It's all just a waste of time. I wasted maybe a year and a half too with it, don't bother. But the basic idea, this SWA thing, which is what they have here, what they did in Russia, was that usually what happens is like if you're working with a high learning rate, you kind of miss this point here. So at some point they'll have like the learning rate will start here and then they'll drop it and then they'll drop it again sort of thing. And these guys from Russia, they basically decided just to kind of keep it up higher, but just to average the points. That's why it's called stochastic weight averaging. So it's just a trick. Atom, what it basically tries to do is by seeing each of your parameters, so your gradient is some big vector, right? And so here you have like parameter 0, parameter 1, parameter 2, da-da-da. And so because it's like very high dimensional, right? So it's not just like one dimensional like this, there's another dimension here and goes on and on and on. If you have just like one global learning rate, you might be basically moving too much in these big ones or too little in these flat ones. So you try and kind of adapt that. This is the idea of like, that's what's called adaptive optimization. And Atom is like the most famous one, right? And this is just here like some trick to how you use weight decay. And all the ones here are just basically Atom with some trick. We just gave it a cool letter because we thought like Atom X just sounded more cool. But I could have called it Atom W with weight averaging. But I was just trying to be fancy and brand myself. But so for the practical people, just use SGD. Don't bother with anything else. Did that answer your question?
Yes.
Anything else? Okay, I think we're done. Thank you for coming.
Maybe you could some other business cases.
Oh, unfortunately, no.
Maybe something unsolved.
Well, there are many unsolved problems with what I'm doing now, right? So, but that ends up being, so the thing that I showed here, right? This here was just basically me applying some domain knowledge, right? So I go to the gym, I trained a lot, I trained at a reasonably high level, I competed for my university. A lot of people that trained with me ended up quitting because of back problems. Most people actually that train encounter some type of back problem. And so when do they encounter, well, they don't really, like when they encounter their back problem is quite hard to predict, but when do you usually see this bad like posture in the movement? That's usually like as soon as you start lifting. That's when people like tense up and they do this, right? And so this was really just a combination of algorithms to get things to work. I knew what I was looking for, right? I knew I can see it, that's bad. The question is just like how I make that into an automated process. So there was actually like a few algorithms that went together. So specifically what I had was I had this one here. So it kind of detects your repetitions. And then once you've started on this repetition, that's about here when it starts to measure the back, right? So it just hones into that frame there, right? And then I apply what I've just discussed using the contour of the dense bow. So this is like one thing here. But like any trainer or any person might have other things they're looking for. It's a question of how you, in my view, can like program that. Now, why do I want to program that in that way instead of use artificial intelligence? It's just because I don't want to be so data hungry. If I had hundreds of thousands or millions of videos that were labeled by good trainers, then I could just chuck a big neural network at it and it would just give me an answer. I don't have the data or the resources to do that. So I'm trying to be super cheap, basically. So that's like one problem. Why? Did you have something in mind?
I'm a technical engineer by my first degree, and I'm thinking about some sensors in his neck.
Yeah, so this is the point, right? So why did I have this idea, right, in the first place? So even for something as simple as just tracking your velocity, people that I knew were spending like $500 buying like a velocity tracker. And so my first project was actually to prove to this guy that what I did on my computer could be equally good. And you can just run it on the phone for free. Right? So that was kind of like the product innovation, is that we already have the GPU or neural processing unit running on the phone unused, and I just need to program on that to get the stuff, right? So this is the point, like, why do I need sensors if I have everything in the video? Anything else? Go on.
Why didn't you connect intersection points on your back to like find out if the back is curved?
What do you mean by intersection points?
You see your back is like there's different lines, and you see like in the middle they connect. Like
where?
Like intersections on the grid.
Yeah.
Uh-huh.
So you can take all that intersection points in the middle of your back. Just you'll have like a diagram, and you'll see. And if you know if your back is like this, and that's not good either.
So basically, by looking at the area of these squares.
Yes.
So that's actually not a bad idea. The reason I went against that is you cannot see it on this because this doesn't connect to the video that I had in my slides, but I do have the video, is that these lines are actually not that stable frame to frame. So I would have had to do more work to basically get denspos running. So all I did was basically run denspos on all the frames sequentially. Now, if I'd wanted these things to be stable, I'd have had to find a way to smooth it or a way to make it more stable through that process. And I just judged it to be easier to do what I did. Because I want to get it working. But that's not necessarily a bad solution. That might work, that might even work better. It's just when these lines are all moving around, you know that that isn't going to work so well. So one frame, so for example, my method is very stable frame to frame. For this to be stable frame to frame, I'd have to do some quite deep changes to denspos, because denspos has already been trained on these thousands of images on many, many GPUs, so I can just use that pre-trained model. I would now either need a way to smooth out the lines frame to frame, in which I would then lose information over the movement, or I try another method. But that's not a bad idea. These are all things you try out. Anything else?
You used PyTorch by Python?
I used TensorFlow before I moved to Russia 2 or 3 years ago, and it was a terrible, terrible experience for what I needed. I mean, apparently it's better now. But yeah, I think PyTorch, I'm just used to PyTorch now.
And Google Colab or no?
Not for training this. Google Colab times out a lot. And I have more power to my disposal than that. But Google Colab's pretty good to start with, yeah.
And what are the more powerful than Google Colab?
Well, I just have Huawei computers. I have like 8 GPUs to myself. No timeout, no stress.
And how long did you train?
I only trained the weight segmentation model. And this I trained on a 4 gigabyte GPU, just my laptop, for like one night. So it was a cheap solution. Yeah. Cool, anything else? All right, thank you everybody for coming, and have a nice night. And